hopefully you've had an opportunity to try out this problem on your own. I'm going to walk through the solution here. We are working with iron 56, and we want to calculate the binding energy per nucleon. So whenever I see an isotope, the first thing I do is try to interpret it into what is my nuclear structure. And so for iron 56, that's how our isotope is written. I can convert that into an isotope symbol if it's easier, where I place that mass number in the upper left-hand corner. And then the atomic number for iron can go in the bottom. And that atomic number is 26. So that means I have 26 protons and 56 minus 26 neutrons, which is going to be equal to 30. So I can use that information along with the mass of a proton and neutron to calculate the mass that the nucleus would have if there wasn't a strong force that was stabilizing it and converting some of that mass to energy. So to get to that binding energy per nucleon, I first need to find the mass defect. So I'm going to calculate that by first taking the sum of those different particles. So I've got 26 protons, which I'll multiply by the mass of a proton, which is 1.00783 atomic mass units. And I'll add to that 30 neutrons, so 30 times the mass of a neutron, 1.00866 atomic mass units. I'll take the sum of that and subtract the mass of the nucleus for just this nuclide, which will be the 55.93494 atomic mass units that's given to me. Now, with that information, I'll calculate this just by plugging into my calculator and get 0.052844 atomic mass units. All right, so that's my mass defect. That's my mass that seems to disappear because it's converted into energy. Now I can take that mass defect and convert it into energy. And so that's going to be my 0.052844 atomic mass units I just calculated times that 931.5 mega electron volts per 1 atomic mass unit. And now I'll be in units of energy, and I'll report my answer in mega electron volts. I could also from here convert to joules as well. So that's going to give me a value of 492.24 mega electron volts. All right, so from there, I can actually calculate the binding energy per nucleon. So that binding energy is going to be equal to the mass defect divided by the number of nucleons. And so I just calculated that that is 492.24 mega electron volts, and I'll divide that by my 56 nucleons, which will give me a value of 8.790. And you'll get a value of about 9 if you instead use a different value for the proton mass. But so you'll get a little range between this and about 9 mega electron volts per nucleon. And this iron 56 is actually our highest binding energy that we have out of the periodic table. And so this really represents our most stable nucleus that we have.